This is the third video about equilibrium calculations. We are knee-deep in ice tables right now. We have done a simple problem where we had to solve for the equilibrium coefficient, equilibrium constant, excuse me. We did a difficult example in the last video where we had to solve for the equilibrium concentrations and do a serious amount of math. And now in this third example, we're going to solve for the equilibrium concentrations again, but I'm going to show you a second shortcut that you are sometimes allowed to use that will speed up your calculation process. All right, so this example wants us to find the equilibrium concentrations for a solution that is 0.25 molarity of ammonia initially, and the Kc value is 1.8 times 10 to the negative fifth. And we can see that I have written this line twice for some reason, and that we've been given the balanced reaction. This is one of the ones we used for practice back on the shift video. And so we've only been given one concentration, so this is going to be a very interesting problem that we have to solve. But we're ready, because we know the 4 steps. So the first step is to determine the shift direction, so we need to solve for Q. So Q is going to be products over reactants, so we're going to have NH4 plus to the first, and OH minus to the first. And both of those are going to be the initial concentrations. And then for reactants, we're going to have NH3 initial to the first. And then remember, water is a pure liquid, so it's not going to get included in the K or in the Q or in the ice table. We still love water, just not enough to include it here. So no water. All right, and then we're going to plug in the numbers. All that this problem says is it's a 0.25 molar ammonia solution. That's all that we know. So if they don't tell us anything about the products, that means that we don't have any products initially. And they did tell us about this one. They said ammonia was 0.25 molar. But it doesn't matter, because if we don't have any products, 0 over anything is going to be 0 for our Q value. And like we talked about in one of our other examples, if Q is equal to 0, Q is always going to be less than K, and we are always going to shift to the right. Okay, not so bad. Step 2, filling in the ice table. So we'll set up our ice table, ice along the side, reaction along the top, including the states when I do it, just to make sure I remember what not to include in the table. There we go. We'll separate the reactants from the products, and we'll draw a line between C and E so we remember to add. Okay, so initial information, all we have is this one number for ammonia, 0.25 molar. So we'll assume that there are no products present at the beginning. And we're going to ignore the water, so we're going to put a squiggle. Technically, if you're going to be ignoring something like water, you don't have to put it in the ice table. I just like to put it in the ice table so that I have my totally balanced reaction up at the top. And then I just draw the squiggle to remind myself not to write anything here. Okay, so the C line is the change. That's where our shift goes. We shift to the right. So we're going to subtract the reactant side, and we're going to add to the product side. Each of the coefficients here is going to be 1. It's going to be 1x all across. And then we don't have any information about the equilibrium, which we usually don't, spoiler. So we'll add down 0.25 minus x molar, and x molar, and x molar. All right, this one is looking significantly simpler in terms of math already. All right, step 3, solve for x using our K expression. So K is our equilibrium constant. It is going to look very similar to Q. but it's going to be the equilibrium concentrations this time. Okay, and for our equilibrium constant, we're going to use our equilibrium concentrations. So for NH4, the concentration is X. For OH minus, the concentration is X. And for NH3, the concentration is 0.25 minus X. And then for our KEQ, we were given that in the problem, KC, 1.8 times 10 to the negative 5. So there's our math problem that we need to do to solve for X. So now, this is where we started doing our math, and we started doing our rearrangement to prepare for the quadratic last time, but this time we're going to do something different. So we'll put a stop sign. Time to use our handy dandy approximation. All right, so here's how this approximation is going to work. We are going to assume that our unknown X, the amount of change, is much, much smaller than that initial 0.25 molarity of the NH3. And if we assume that's true, that means that that term in the denominator, the 0.25 minus X, if X is way, way smaller than 0.25, then this 0.25 minus X is essentially just going to be 0.25. So we can essentially eliminate or ignore that X. So, disclaimer, you can only use this assumption when you have an X that is added or subtracted. So if we were to have something multiplied by X, we are not allowed to get rid of it. We can only get rid of it when it's being added or subtracted from a number. So don't get too excited. All right, so we're going to say we're going to ignore that X. So let's do step 3 again. KEQ equals X times X divided by 0.25. And we're going to ignore that other X on the bottom. And that is equal to 1.8 times 10 to the negative 5. So now we're going to do the same thing that we did last time. We'll write that KEQ over 1, and we'll cross multiply to solve for X. Okay, so we're going to have X squared times 1 equals 0.25 times 1.8 times 10 to the negative 5. And I've already noticed that this looks way easier than that quadratic expression that we had last time. This quadratic expression only has one term with an X in it, and the other term doesn't have an X. So we can solve this without using a quadratic equation. We can just take the square root of both sides to get our two values for X. So X equals 0.00212 molar, or our other value for X is negative 0.00212 molar. First of all, wow, that was so easy. I didn't have to use the quadratic equation. I did have to use my calculator, but only briefly. Second of all, I can already tell which one of these values for X is not going to be a good one. I can see that the equilibrium concentration for NH4 plus and for OH minus is equal to X, and those concentrations cannot be equal to a negative number. So I can already tell that I'm going to cross that one out So x1 is going to be my man. So that was amazing. So easy to solve that problem. But now we need to stop again. Because using that assumption comes with consequences. So when we use an approximation and we cheat and we leave out a number, we leave out an x, it introduces error into the system. And as we know from our general chemistry laboratory, a little bit of error is okay. No one's perfect. But at some point, if the error becomes too large, that means our number is not really a useful answer at all. So we need to check whether our approximation error is okay. And so we're going to be okay with 5% error. We're going to be generous. We're going to say 5% error is not that bad. So the way we're going to check the error is we're going to take the number we found for x that we decided on, and we are going to divide it by the number that we assumed it was way smaller than. So I assumed that my x was way smaller than 0.25. And I wasn't going to write 0.25. I was going to write the initial concentration of A. That's where this number came from. The initial concentration of this thing, I assumed it was much larger than x, so now I'm going to test whether it is actually much larger than x. So I'm going to take x over that number, and I'm going to multiply by 100%. If this number that you find is less than 5% error, that's okay. Less than 5% error is acceptable. We're willing to put up with that to not have to do the quadratic equation. But if this number is greater than 5%, then you're going to have to go back and do your foiling again with the full equation with the x in it and the quadratic equation. So this is not necessarily a time saver if you guess you can use the approximation and you discover that it isn't. But in my opinion, doing it the easy way and then checking to see if you're allowed to cheat and then having to go back and do it the long way is still better, because at least 50% of the time you're going to save yourself from doing the quadratic equation. So I'll shut up now and we'll find the answer. Let's do our approximation check. So our x value was 0.00212. We assumed that x was much, much smaller than 0.25. So let's see if it really is or not. Multiply by 100%. Math happens here. That's going to give us 0.008% error. And I don't know about you, but I would call that super duper good. I have never done an experiment and done that well. That number is definitely below 5%. So our approximation is okay. So we can keep that number that we got using the approximation. So now we'll go to step 4, and we'll answer the question, which was asked twice. Find the equilibrium concentrations. So that means we want to find the numbers in the E line of the table. So our equilibrium concentration of NH3 was 0.25 minus X. So that's going to be 0.248 molar. We are running out of space on the page. And the equilibrium concentration for these two guys, NH4 plus and OH minus, those are the same. They're both equal to X, and X was equal to 0.002 molar. There, we fit it on the page. All right, one more review of what has just happened here. We found our Q and our shift direction. We set up the ice table and filled it out. We plugged in our numbers for K, and we decided to use an approximation and assumed that in this add subtracting X term, that X was much smaller than the number it was being added or subtracted from. And we left it out. We solved the problem for x, assuming that x was super small. We found a super small number. Then we checked our error to make sure that x was much smaller, less than 5% of that number. It was 0.008%. And then once our approximation was confirmed to be okay and legal, we used our x to answer the question and find the equilibrium concentrations. So I will say it again. By using the approximation, you will occasionally cause yourself to have to do extra work, because if you check your approximation and discover that the error is greater than 5%, you will have to go back and do the quadratic equation again. But on the bright side, if you do the approximation, you will save yourself the trouble of having to do the quadratic equation for some of the problems you do. And in my opinion, if you can save yourself from having to do the quadratic equation, it is an approximation well made. So that should be everything you need to know about ICE tables for this initial introduction to them. We'll have more in the next chapter, and we have a little bit more content left to relate our equilibrium constant K to Gibbs free energy in the next video.